We've learned a lot about how to construct features and approximate functions. But that was all in the context of making predictions with a fixed policy. This week we'll talk about control with function approximation. In this video, we'll start with the GPI algorithm, Episodic Sarsa. By the end of this video, you'll be able to understand how to construct action-dependent features for approximate action values, and explain how to use Sarsa in episodic tasks with function approximation. Recall that the value function approximation has two components, a weight vector and a feature vector. In a given state, the value estimate is the dot product between these two components. To move from TD to Sarsa, we need action value functions. So the feature representation has to represent actions as well. One way to do this is to have a separate function approximator for each action. This can be accomplished by stacking the features. That is, we can use the same state features for each action, but only activate the features corresponding to that action. To understand this more clearly, let's look at an example. Let's say there are 4 features and 3 actions. The 4 features represent the state you're in. But we want to learn a function of both states and actions. We can do this by repeating the 4 features for each action. Now the feature vector has 12 components. Here, each segment of 4 features corresponds to a separate action. We call this feature representation stacked because the weight for each action are stacked on top of each other. Thus, only the features for the specified action will be active, while those for the other actions will be set to 0. Let's see an example of how to calculate the action values from a given state. Let's say that there are 4 features and 3 actions. The weight vector looks like this. With stacked features, we get the following feature vector for action 0 in state S. We zero out the features for the other actions. So we extract the segment of the weight vector corresponding to each action. The action values are then the dot products between each segment of the weight vector and the feature vector. You might think that stacking features to create action values is specific to linear function approximation, but this is not the case. For example, the common way to represent action values with a neural network is to generate multiple outputs, one for each action value. This, however, is equivalent to the stacking procedure we just described. The neural network inputs the state, and the last hidden layer produces the state features. Each action value is computed from an independent set of weights using those state features. The weights for one action value do not interact with those of another action value, just like in stacking. We might want to generalize over actions for the same reason generalizing over state can be useful. Now, how might this work with a neural network? We would input both the state and the action to the network. There would only be one output, the approximate action value for that state and action. We can do something similar with tile coding by passing both the state and action as input. Okay, we now know how to handle action values with function approximation. Let's talk about using Sarsa for control with function approximation. The algorithm is quite similar to the tabular version, so we will just review the differences. We use parameterized action value functions for the action value estimates. The update also changes to use the gradient to update the weights, similar to semi-gradient TD. And that's it. That's the Sarsa control algorithm with function approximation. In this video, we talked about action-dependent features, and we introduced episodic Sarsa with function approximation. We will cover a few more control algorithms in the coming lectures. Until next time,